So in the previous class, we started discussing about the neutral point voltage deviation, especially in diode clamped multi-level inverters. So what mainly we observed that the current is flowing into the neutral point. So therefore, there will be deviation in the charging and discharging of the capacitor voltages, right? So this deviation will introduce a DC offset in the output voltage waveform. Okay, and moreover, if it is drastically varying, for example, the deviation is very large, so in that case it will altogether affect the performance of the inverter drive. Once again, so there will be some flow of neutral current, so that's why there is a deviation in the voltages, right? Okay, so our objective is, there is another right, so there's the deviation, there is another one is some manufacturer tolerances. For example, this capacitor and this capacitance are okay, so even though they are of same manufacturing company, so there will be some tolerances in their values. So usually it will be plus or minus. So 1 second. Yeah. Okay. So there are manufacturing tolerances. Okay. So those tolerances, usually we have different types of capacitors are there, right? So we have ceramic capacitors, we have capacitor with polypropylene capacitors will be there. Okay, so they have some tolerances will be the electrolytic capacitors. Most of the cases we prefer the electrolytic capacitors. So electrolytic capacitors, we have some tolerances. The tolerances is in the order of plus or minus 5% or plus or minus 10% range. Okay, so there will be some deviation in the voltages, deviation in the charging and discharging periods also. So that is also created unbalance in the capacitor voltages, right? So another one is the inconsistency in the switching characteristics. So there is inconsistency, as we already discussed that. So when you require one voltage, so if you continuously turn on this or if you continuously turn on this voltage, or if you continuously turn on the upper one or the lower one, right? So that is causing some inconsistency in the capacitor voltages. So another one is the unbalanced operation. For example, if this load is not balanced, so that is also cause the neutral voltage deviation. So that is also cause neutral voltage deviation if the load is unbalanced. So there are three possibilities. The first one is the unbalance in the DC capacitors due to manufacturing tolerances. The second one is the switching pattern, and the third one is the unbalance in the load side, or in other words, unbalanced operation of the inverter. So these three cause the capacitor voltage to deviate, right? So when you are using the space vector modulation technique, so you must, or when you're using any control method, you must ensure that these two capacitors must be balanced, right? So here the disadvantage with this diode clamp multi-layer inverter is there is no switching states, or there is no switching redundancies. So if you require one voltage level, so you have only one path, right? But the thing is that when you use the space vector modulation technique, so we have some additional switching states available, right? So these are in this form. So these small vectors, right? So there is some switching redundancy is there. So either you can choose this p-type small vectors, or we can choose this n-type small vectors. Okay, so this is the advantage with space vector modulation. So if it is no switching redundancy in the actual operation of the circuit or actual operation of the inverter, but the space vectors created some switching redundancy. So this is the one advantage with space vector modulation techniques, in addition to the increase in the fundamental RMS value, or in other words, increase the DC utilization ratio. So if here, in case of zero vectors, there is another three possible redundancies are there. So it is PPP, 0, 0, or NNN. In case of small vectors, we have two pairs of redundancies there. And in case of medium vectors, there is no redundancy here. So here also there is no redundancy, right? So once this is over, so our next step is how to identify, or how this medium vector, small vector, or large vector will affect the neutral point voltage. So that we'll study now. So we'll start with this small vectors first. So we have p-type small vector and we have n-type small vector is there, right? So we have p-type small vector is there and n-type small vector is there. So let us consider, if you have p-type small vector, let us consider pp0 in one case and n-type small vector. So at the same time, n probability is 0, 0, n. Right. So let us see. So how it will impact the capacitor voltages in the neutral point. So that we'll study now. Right. So we have inverter is there. So it will basically perform two kinds of operation. It may be motoring mode or it may be regeneration mode. Right. So in other words, the current is away from the inverter or the current is inside the inverter, right? So in other words, that is a positive current and the negative current, right? So let us assume that, so we have, right? So let us assume that the current is going away from the inverter. So that means it is motoring mode. So the current is going away from the inverter, right? So we have these capacitors. So we have C1 here, CT here. So this is the midpoint of the capacitor. So this point is O, that is neutral point. And this is connected to the DC link. And this voltage is, which is VDC. So this is the one we normally call as neutral point voltage. So VZ. So this VZ is the neutral point voltage, VZ. So most of the cases we denote with Z, right? Neutral point voltage Z. And this is positive DC bus and this is negative DC bus. All right. So we have load here. So load is having three terminals. So this is A phase, B phase, and C phase. So we already discussed in just previous class. Okay. So our ultimate objective is to connect this load via the switches, right? So we have A phase leg is there, B phase leg is there, and C phase leg. So by operation of appropriate switches, so we need to turn on the inverter, right? So we have this PP0 operation. So what is its meaning? Right, we'll start with P type PP0. So what is the meaning of this? What is the meaning of this PP0 switch state? So what is A phase polarity, B phase polarity, and C phase polarity? What it means?
1, 3, 2.
So if A phase, this is A phase, B phase, C phase, right? So that means A phase is connected to the positive
Switch.
DC bus, right? Agree? And similarly, PP0, so means A phase is connected to positive DC bus. Similarly, this is also P. So that means this B phase is also connected to the positive DC bus. And whereas the C phase is connected to the neutral point Z or the zero voltage. Right. In case if it is N means, so this is connected to the negative DC bus. So that means this is connected here. Understood? So now this is the one. So this is connected to A here and this is connected to B. Right. So what is the fate of this one? So this is Z. So this C phase is connected to this point. Understood? Understood? So this is the equivalent circuit for PP0 switch state. All right. So now, so let us mark the current. So this is the current. So we assume that the motoring mode, right? So the current is flowing, or we assume that the normal operation. Okay. So that's a normal operation. So that means the power flow is from source to load. So this current is flowing like this, and this current is also flowing like this, right? So which one is providing the return path? The C phase is providing the return path, right? So this current is flowing like this. Agree? This current is flowing like this. Understood? So now what will happen? Right. So now what will happen? So which capacitor is charging and which capacitor is discharging? So which capacitor is charging and which is discharging here?
C1 is
C1 is
discharging.
discharging, C2 charging.
C2 is
CT charging, right? See, if you observe that, so whatever the amount of power that required for the motor or required for the load, so that is supplied from the C1, right? And the CT is acting as a return path. So if you observe that this current flowing is inside this like this, and this is the current flow. Agree? So we already discussed that if a positive current is flowing like this, that means the particular capacitor is discharging, and this particular capacitor is charging. So here, okay, so near, so this is voltage across C2, voltage across C2 over VZ, right? So VZ is having some value. For example, earlier if it is 400 is VD, so this is 400. So this is supposed to be 200 volts, and this is supposed to be 200 volts, right? Okay. So now, so VD value will increase or decrease? So VZ value, so will it increase or decrease? Increase. So what will happen? So this capacitor charging,
increase.
right? So therefore,
Increase.
so this VZ value will be increased. All right. So this VZ value will be increased. Okay. So we have deviation in the neutral point voltage. So this P type or this PP0 vector, so that is causing deviation in the neutral point voltage. So what kind of deviation it is? So it is increasing the neutral point voltage VZ, right? Similar case, so we'll consider one more or another type of P type vector. So that is another one is P00. Okay, so let us consider this is another P type vector. So we have load here, right? So P00, so that means this is connected to here, agree? And these two are connected to here. Understood? So this is your VZ. So here, so this current is flowing like this, so like this, and it is acting as a return path, like this. Agree? In other words, we are never sure, right? So how exactly it will flow, but thing is that, so it should be the return path for this. So now what is the fate of this VZ? So will it be increased or decreased?
Increases.
So VZ is increased, right? So VZ is increased, right? So what we understand that we have another some more p-type vectors are there, right? There are 6 p-type vectors are there, right? So starting from P00, PP0, 0P0, 0PP, 00P, and P0P. So all are having the same, more or less same equivalent circuits. That means one phase is connected to positive DC bus, and one or two phases are connected to the positive DC bus, or one or two phases are connected to the neutral point. So therefore, since all the p-type small vectors or all the p-type small vectors, in case of motoring mode, so this neutral point voltage is increases, right? So that neutral point voltage is increased. Similarly, so now we'll come to so next one. So that is n-type small vector. So in case of n-type small vectors, we consider So N type 00N. Right. So this is the equivalent circuit again. Okay. So this is your neutral point, and this is VZ. So this is connected to 0. Agree? So this is also connected to 0. Right. And this point is connected to negative DC rail. Understood? Right. So now, we already said that this is the positive current. So the current is flowing like this. The current is flowing like this. Okay. So what is the written path? So how the current is written? So the current is written like this. Okay. So that means the current is flowing like this, right? So it is flowing like this. So therefore the current is flowing inside this one. Agree? So now, so what is the fate of this VZ?
Discharging.
Increases.
So will it be increased or decreased?
Increases.
Decrease.
Decrease.
So it is decreasing, right? So it is decreasing. Okay. So what you understood that, so p-type vectors increases the neutral point voltage and the n-type vectors decreases the neutral point voltage. Understood? So p-type vector will increase the neutral point voltage and decrease the n-type vector will decrease the neutral point voltage. So remember, so all the things we are doing for the motoring mode, that means the power supply is from the source to load, right? So if it is from load to source, right? For example, same thing, so same case. I'm just removing this. In the same analysis, right? So let us assume that, so this is generating operation, or if it is operating in regen mode, or right? So in case of regeneration mode, so what is the current here? The current is flowing from load to source, right? The current is flowing from load to source. So that means it will be like this. Agree? And here, so this means, so it will be like this. So now tell me what is the fate, so what is, so VZ will be increased or decreased?
Decrease.
So VZ is decreased, right? So this capacitor C2 is feeding the load, right? So that means whereas the regenerative energy, so that is used to charge the capacitor C1. The regenerative energy, so that is used to charge the capacitor C1, right? Similarly here, so in this case, this is the case, and this will be the case, right? So this is the case, and so in this case, so what is VZ? So what is VZ now? So will it be increased or decreased?
Increase.
So this capacitor now it is charging, right? So that means it is increased. Okay. So what we summarized that, so during the normal operation, the p-type small vector increase the neutral point voltage and the n-type small vector decrease the neutral point voltage. Okay. And it is vice versa for generating mode of operation. And it is vice versa for generating mode of operation. So that is the conclusion about this p-type small vectors and p-type and n-type small vectors, right? Similarly, if you have medium vectors, medium vectors. So we had different medium vectors are there, right? So what is one medium vector? So medium vector consists of all the three, right? So let us consider N0P. So medium vector N0P. So one example, right? Right. So this is the point here. Okay. So how these phases are connected here? So this is N0P. So N0P. So that means this is A phase, B phase, and this is C phase. Okay. So that means A phase is connected to the negative. So this is A, right? And B phase is connected to this point. So this will be your B phase, and this will be the C phase. Understood? So now we assume that the positive, that means the normal operation. So let us assume that the current is flowing like this. Okay. So now the current is flowing like this. Okay. So how the return path is provided? So how the return path is provided? So how the return path is provided in this particular case? So how it is provided? So can you determine? So can you confidently say? So this is the direction of current. Can you confidently say? So this is the direction of the return path.
No, sir.
So if this is the incoming current, so we cannot confidently say the current is right. So that means the current is coming out of this like this, or the current is flowing in this direction, right? So because two phases are there, so that means A and B phases are right. So depending on their instantaneous values, so in which phase the current is exactly right, the current is exactly coming out, so that can be so determined. So therefore, the thing is that we cannot say that this current is flowing in this direction or in this direction, but definitely there is a flow of current. All right. So because the C phase is split into A phase, C phase current is split into A phase current and B phase current. Okay. So but their instantaneous polarity, so that all depends on their instantaneous voltages. Right. So therefore, we cannot confidently say that the current direction. So therefore, the current may be charge the capacitor, or current may be discharge the capacitor. The current may be charge the capacitor or discharge the capacitor. So that means, but it will affect the neutral point voltage. So that means here the current is flowing inside this neutral point or away from the neutral point. But definitely, so it is affecting the neutral point voltage, right? So how it is affecting, so that is undefined. So that is undefined. So here, so this Vz is affected. Okay. So Vz is affected. So but we cannot determine that. So that means not determined, or in other words, not defined. So we cannot comment on that, so whether it is increasing or decreasing, but definitely it is affecting. So this is case with the medium vector in case of motoring mode. So in case of generating mode, the same case in case of generating mode. So we'll discuss here itself. So let us consider this is P0n vector. So now it will be A phase, so it will be B phase, and it will be the C phase. Okay. So that means the current is flowing like this. So generating mode, right? So the current is flowing like this. So this is regeneration, and this is normal operation. Okay. So here also, right? So A phase, the current is moving away from the A phase. Okay. So therefore, the return path is provided by B phase, C phase. So it may be any of one of the phase or both phases. So therefore, here also the current, neutral current may flow in this direction or in this direction. So that means this Vz is undefined. So certainly it is affecting the neutral point voltage. So how exact it is affecting? So that is undefined in both operations, either in normal operation or in regeneration operation. Okay. All right. So now come to the large vectors. Large vectors. Right. So large vectors means it consists of all. So that means Pnn. So let's assume that this is the large vector. So it consists of P and n terms only. So we have load here. And this is your neutral point voltage, so Vz. So what is the meaning of this P and N? So A phase is connected to the positive DC bus. So A phase is connected to the positive DC bus. This is A, right? And B phase and C phase are connected to the negative DC bus. All right. So A phase is connected to the positive DC bus, and B phase and C phase are connected to the negative DC bus. Right? So now tell me, what is the fate of this Vz? So whether it is increasing or decreasing or remains same. So will it increase, decrease, or remain same?
Remains same.
So if you assume that this is the normal operation, so that means definitely the current flow, so it will be like this, right? So as we already discussed that if there is a current flow inside the neutral point, so then only it will affect. So then only the neutral point voltage will be affected, right? So here there is no current flow towards the neutral point. So therefore, so this Vz is unchanged. Agree? This Vz is unchanged. Or in other words, it is not affected. So it is not affected. Right? This unchanged means, so with this it is unchanged. So there is certainly there are other changes, or certainly there are other things so that may change, but certainly this large vector, that is not changing the neutral point voltage. All right. So this is for normal operation. So in case of regenerative operation, So let us assume that we have another one. So that is NPP. So the another one. So that is NPP. Okay. So meaning of this N. So it will be the C phase, right? So now this BN. So no. Yeah, this is C phase, and this is also A phase is also connected here positive, and this will be the A phase. So A phase is connected to the negative, right? Okay. So here this current is like this. That means this is the current direction. So here also there is no current that is flowing inside the neutral point. So that means this Vz is unchanged. So this Vz is unchanged. So what we understood that small vectors will change the neutral voltage, right? Either it will increase or decrease depending on the p-type vector or n-type vector and the direction of the current. Medium vector will definitely change the neutral point voltage, so but is undefined. So whether it is increasing or decreasing, so that is undefined. But the large vectors will not affect the neutral point voltage, right? Similarly, one more thing, so that is missing. So that is zero vectors. Okay, so those are the zero vectors. So now we'll see how these zero vectors are. So we have three zero vectors, P, 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 0, 0, 0, and N, 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 right? So zero vectors. Okay, so we have this P, P, P vector, right? So what is the meaning of this? So all A phase, B phase, C phase, so that is connected to the positive DC bus. Okay, so that is connected to the positive DC bus. So this is your positive DC bus. So this is A phase, B phase, and C phase. So all are connected here. So A phase, B phase, C phase. So all three are connected here. Okay. So what is its meaning is that? So what is the meaning of this? So that means A phase, B phase, C phase. So that is short circuited, right? Understood? So A phase, B phase, C phase are short circuited. That means A phase, B phase, C phase, 3 phase are all are connected. So that is providing a closed loop for the load circuit, and it is not delivering any current from the source. So there is no current. So that is flowing here from this source. Right. So now will it affect the neutral point voltage? So will it affect the neutral point voltage here? Hmm? Okay. So here this is never, it's not at all delivering any current from the load itself, right? So that means, so there is, it is, this Vz is unchanged. So there is no change in the Vz. Okay, right. So here the load terminals are short circuited, and that is connected to the positive PC bus, but there is no return correction to the source, right? So therefore it's, the load is freewheeling, right? So therefore, so this Vz is unchanged. So this is for PPP. Similarly, if it is for 0, 0, 0, so in this case, thing is just simple, right? So this is the case. Agree? So this is for 0, 0, 0, and similarly N, N, N. So this is just simple. So we have this negative DC bus. So B phase is C phase is connected. This B phase is connected, and this A phase, this is also connected. So here also there is no current from the source. So therefore this Vz is unchanged, even though if it is a motoring mode of operation or the regeneration, or even though it's a normal mode of operation or the regenerative mode of operation, so there is no change in the neutral point voltage. Understood? Okay. Right. So with all this theory, okay, so with all this theory, so what we have to do is, so we need to use these things, right, especially the small vectors, to balance the neutral point voltage, to balance the neutral point voltage. Okay. So we already discussed the space vector diagram for the 3-level inverter, right? So it is, so this is space vector diagram. So we already discussed this. So each vector is divided into 4 regions, starting from 1, 2, 3, 4, right? So here in each case, right? So each case, so we have, so each right. So once this is done, and we also calculated the dual times or the timings for TA, TB, T0 or TA, TB, TC in different sectors and different regions, right? So first we need to identify the sector, and next we need to identify the region. Okay, and after that we need to identify the nearest vectors. So based on the nearest vectors, so we need to calculate the timings TA, TB and TC, right? So once this is done for all the sectors and all the regions, okay, so next thing is we need to arrange the switching sequence. So next thing is we need to arrange the switching sequence. All right. So we need to arrange the switching sequence. Okay. So here also we have some constraints or our own constraints, right? The first thing is that the transition from one switching state to next switching states, right? So for example, if you applied V1 vector and after that we need to apply V0 vector or V2 vector, that means transition from one switching state to another switching state. So that involves only one transition of the switch. So that means one being turned off and the one being turned on, right? So this is the same constraints that we put for 2-level inverters. The transition from one switching state to the next involves only one phase or one pair of switches affected. So one being switched on and the other being switched off, right? Another one is the transition of V reference. So V reference when it's moving from one sector to other sector. So for example, it is moving from sector 1 to sector 2. So there will be no switching or the minimum switch or minimum number of switchings. So when it's changing from one sector to other sector, so you have to make sure that so there will be no switching change in the vector, right? So that means the simple thing, for example, this is V14. So that is the last switch state, it's applied in the sector 1. So that means the sector 2. So when you apply the firing pulses for the sector 2, so that means it start from PPN. So that means V14 vector. So we need to apply again, right? So that so there is no transition in the there is no transition, right? So another one, so this is in addition to the 2-level inverter. So when you're doing so or when you're designing the switching state, so we need to make sure that or we need to concentrate that the switching or we need to concentrate that the neutral point voltage must be minimized, or the deviation of the neutral point voltage must be minimized, right? The neutral point voltage must be minimized. Okay. So now, so before discussing this or before arranging the switching pattern, right? So before arranging the switching pattern, so let us consider, so let us assume that this is in sector 1 and this is the V reference vector, right? So now we already discussed that this is the V reference vector. So what are the nearest space vectors? So we have V1 vector is there, so V2 vector is there, and V7 vector is there. So we have 3 nearest space vectors are there, right? So one is V1, V2 and V7. Okay. Right. So now come to our theory. So what we discussed is that, so our objective is to reduce the neutral point voltage deviation, right? So now, so this V1 is a small vector, right? And this is also V2 is a small vector, and this is medium vector. Okay. So now the thing is that, so we can right? So we can control the neutral point voltage. So by using these small vectors. So how to control the neutral point voltage by using the small vectors? So let us assume that. So here we calculated the time that is required to operate this TC. This is the TC period of time. So we need to operate this. Okay. So this TC period, so we can divide it into 2 or 3. So that is TC by 2 and TC by 2. All right. So that means this TC by 2. Okay. So this 1 TC by 2. So here you apply, so this P type small vectors PP0. And rest of this TC by 2 you apply this N type small vector. Okay. So let us assume that if this P type small vectors, if it is applied for TC by 2 period of time, so there will be, we already discussed that the P type small vector, Vz is increases in case of motoring mode, right? And this N type small vectors, this Vz is reducing. Okay. So whatever the slight increase in neutral point voltage, so that may be compensated by applying this N type small vector. Understood? So that is compensated by applying, so this N type small vector. Okay. All right. Similarly, we can make it either 2 parts or 3 parts, right? Some of the cases we are made it 3 parts, right? So it may be TC by 4, TC by 4, and it may be TC by 2. It may be TC by 2. Similar in this case, so TC by 2 and TC by 2. So we may use P type small vectors. So this is N type small vector, and this is P type small vector again. Understood? So whatever there is slight increase or decrease in the P type small vector depending on the operation, so that is compensated. So when you use the N type small vector of same space vector category, right? So V2 we have 2 options, right? We can choose PP0 or 00N. So that is the advantage of the switching redundancy that is especially created with space vector modulation, and that is particularly used to reduce the neutral point voltage deviation. Understood? Right. So this is the thing we used, right? So now, so come to our discussion. So let us assume that this is falls in the region 2. The V reference is falls in the region 2. So now it is decomposed with, so V2, V1 and V7. So that means you have 2 small vectors. In region 2, so we have 2 small vectors. Similarly, let us assume that, so this V reference is falling in the region 4. So if it is falling in the region 4. So if it is the case, right? So if this is the case, we have V2 vector is there, so which is a small vector. So V7 vector is there, so that is a medium vector, and this V14, so this is the large space vector. So V2, V7, V14, so that means it's composed of small, medium, and large space vectors. All right. So here, so in region 4, it consists of only small vector. Right. So why we are not, so if you notice that when you are decomposing this one, right? So why we are ignored this V7? The thing is that, so there is no pointing in, or there is no P type or N type small vectors for this V7, right? Okay. Similarly, in region 1, for example, this V reference is falls in region 1. So this is decomposed with V1, V2, and so V0. So that means 2 small vectors. That consists of 2 small vectors. Okay. Similarly, if it is in region 3, so if it is in region 3, so how many small vectors? So this is V1 vector, so there is a small vector. So V3 is the large vector, and the V7 is the medium vector. So it consists of 1 small vector. All right. So now once this is done, okay, so once this is the thing is that, so what we understand that, or what we concluded that, so if it is false in the region 1 or 2, right, so we have two small vectors, okay, so if it is false in region 1 or 2, so we have two small vectors. So if it is false under the region 1, right, if it is false under the region 3 and 4, so it consists of only one small vector. Okay? It consists of only one small vector. Right. So another thing is that, so let us assume that, so what we understood that in region 1 and 2, so we have two small vectors. Okay, so let us assume that this is the case. So let us assume this is 60 degrees, right? So this angle is 30 degrees. Okay. So now this is the V reference. Okay. So this will be your V reference. All right. So now what? Right. So now, so this can be decomposed into V1 vector and V2 vector, right? So here, which one will be the dominant small vector? So which one will be the dominant small vector? If you calculate the dwell times, this TA and TC, right? So this TA must be greater than this TC. Okay. So this time period of this V1 vector will be more when compared to this V2 vector, right? So that means this V1 vector in this particular case, so this is known as the dominant space or dominant small vector, right? So this is known as the dominant small vector. Okay. Similarly, if it is false something like this, if this is the case, right? So now this V2 will become the dominant small vector. Okay. So first 0 to 30 degrees. So this V1 will be the dominant small vector, and V2 will be the dominant small vector for the 30 to 60 degrees range. Right. Okay. Similarly, in sector 2, so in region 2, if it is false in the region 2, right? So from 0 to 30 degrees, so this V1 will become the dominant small vector from 30 to 60 degrees onwards in sector 1, right? So that means, so V2 will become the dominant small vectors, right? So once this is known to you, okay, so once this is known to you, so there are, right, so there are different possibilities to arrange the switching states. So one, we already discussed that there's a 7-segment switching sequence, 7-segment switching sequence, right? 7-segment switching sequence. Okay, so there are two cases. We already discussed that. So if it is in region 1 and 2, it consists of two small vectors. It is in region 3 and 4, it consists of only one small vector. So let us assume that this entire thing is for if it is having one small vector. So that means this is useful for 3 and 4 regions. So let us assume that this is particularly for sector 1 and region 4. So this is sector 1 and region 4. So sector 1 and region 4. Okay. So it must be consists of, so what it must be consists of, right? So V2 vector, V7 vector, and V14 vector. Agree? Must be consists of V2 vector, V7 vector, and V14 vector. All right. V2, V7, and V14 vectors, right? So now, so come to this discussion, right? So here, So this is the case. So this is, we have times TA, TB, TC. So the TA, TB, TC is, we divided into 7 parts. So we have time TA, TB, TC. So that we need to divide into 7 parts. Okay. So now we need to arrange this one, right? So when you come to this V2, okay, or when you come to this V7, which is corresponding to this V2, this is V2 here, and this is this is V2, and this is V7, and it will be V14, right? So now this is divided into 2 parts. So this is divided into 2 parts. So whereas this is divided into 3 parts. Okay. So that is one possible arrangement. Okay. So how it will be? So how exactly it will be arranged? So let us start with TC vector or this V2 vector first. So it will start with, so either we can start with N type small vector or P type small vector, right? So let us assume that we start with N type small vector. So 0, 0, N. So which is V2 small vector, and this is for TC by 4 period of time. So we started like this 0, 0, N, and its period is TC by 4. So what comes after this? So can anyone tell? So what comes after this? What comes after this?
V7.
What is the preferred choice? So which one? So we need to select which space vector
V7.
we need to select. V7, right? So if you notice that, so there are 2 possibilities, right? Either we need to turn on V7 or V14. So V14 consists of PPN, and this consists of P0N. So we have, which is, if you observe that this is P0N, this is 0N, right? So that means if you place P0N here, so there is only A phase is affected. So only A phase is affected. This time period is TB, so it will be TB by 2. Understood? So this is V2 N vector we consider. So this is V7 vector. So what is the next one? If this is the case, so what you will choose the next one?
V14.
V14.
V14, right? So V14, this is P0N. So we need to choose PPN here. Right? So what is the time period here? So this is off of the period. So it will be V14. So what is the next thing you can select? So what is the next thing you can select?
PP0.
PP0, right? So that means
V2.
this is PP0, this PP0, right? PP0 here, only C phase affected. So how duration? This is TC by 2, right? So that means it should be TC by 2. And so this is V2 P type small vector. Agree? Agree? So now earlier we consider N type small vector. So now we consider P type small vectors. So what is the next thing? What is the next one? It's supposed to turn on. PP0 is
V14.
over. What next one?
V14.
So what the next? P14, right? That means PPN. So what is its duration? So it will be TA by 2, and this is V14. So this PPN is over. So what is the next thing? What is the next thing?
P0.
What is the next thing? PPN is over. What is the next thing? I'm asking a simple question.
V7.
V7, right? So P0N.
N.
So this time period is TB by 2, and it is V7. All right. So what comes after this? So we have short with this TC by 4 period of time, right? So what is this TC by 4 period of time? So again, so this is
0.
0, 0, N. So this is V2 N vector. Understood? Understood. So this is how we arranged the switching sequence. Okay, so this V2 vector is there, right? So V2 vector is, so we divide it into 3 parts. Okay, so we start with 1/4 part, so with n type mesh vector, right? So we ended with the same 1/4 of with ended or 1/4 n type small vectors. So in between somewhere we have this p type small vector, right? So whatever that incremental change, so using this n type small vector, so that is compensated in the p type small vectors. If you observe that it is tc by 4, this is also tc by 4, that means the total is tc by 2 for n type vector, and the p type vector is ta by 2, right? No, p type vector is tc by 2 again here, this one. Understood? So this is how we will arrange the sequence. So when you have only one small vector, okay, you have only one small vector. So this is the arrangement overall, right? You can see here the same thing, whatever we followed here. So that is the same thing. It is given here. So it started with 00n, P0n, PPN, PP0, PPN, P0n, 00n. Understood? So here 1/4 period, 1/4 period, and this is off period. So this is TA by 2 and this is TB by 2. So this is 7 segment switching design. Okay. So this is most commonly used one, right? So already seen that we have some drawback with this one. So that is also there. So when it's moving from, so this entire thing is followed in sector 1, region 4. Right. Similarly, same kind of thing. So we can implement for region 3 also. If it is in region 3, for example, okay. So if it is in region 3, so if we have one small vector is there, right? Okay, we have one small vector. So here also we can start with p type or n type, right? We can start with p type or n type small vectors. Understood? Okay. So now, so what we had to do, in case if it is false in region 1 or region 2, if it is false in region 1 or region 2, so what we have to do? All right, if it is false in region 1 or region 2, so what we have to do? Right. So let us assume that so there are two small vectors among the selected 3 vectors. That means it is assume this is the one. So v1 vector here, so v2 vector here, and we have this v7 vector. All right. So now, so how to arrange the switching sequence? So that is important now, right? So now we already discussed that. See, if it is in 0 to 30 degrees, okay. So this v1 vector is the dominant small vector from 0, 30 to 60 degrees. So this v2 vector is the dominant small vectors, right? So here again we have divided this into 2 parts. So each region is again divided into 2 parts. So this is 1A region, 1B region. So first 30 degrees and the remaining 30 degrees. Similarly, this is 2A region and this is 2B region. All right. See, in 1A and 1B region, or in 1A and 2A region, so V1 vector is the dominating one. Similarly, in 1B and 2B region, so this V2 vector is the dominant one. Right. So here, the thing is that, okay, so in this case, let us assume the first case 1A and 2A. So this V1 vector, right. So for only the dominant vector, so V1 vector, so we will implement P type and N type. Okay. For the dominant vector, so we'll split that dwell time into T type and, or when we will apply P type and N type. And this is, will not, or we will apply either P type or N type. So depending on the previous switch state. All right. So depending on the previous switch state. Okay. Understood? So only the dominant small vector, so we will apply or we will use either p type or we will apply p type and n type for the dominant small vector. For non-dominant small vectors, so we will either apply p type or n type. Right. So how exactly it will be? So now we'll see here. So let us assume that this is started with, or assume that, so we have the dominant vector, that is v1, right? So now we'll start this same thing. So we'll start with, so what is this one? So we'll start with 0 and n first. Okay, so turn on this for tc by 4 period of time. So we applied v1 en type small vector. Okay. So what comes after this? So what comes after this? So what comes after this? So I selected 0 and n. I started with 0 and n. So what is comes after this?
0 0 n.
0 0 n, right? 0 0 n, right? So this one. So this is having only one change, right? So how we are selecting that? So you must have one change. If you select p0n, for example, instead of that, if you select p0n, right? So we have two changes. So 0 will become p here and n will become 2. So that means two phases are affected. So our objective is to affect the only one phase, right? So that means we have 0 0 n. And what is its time period? So this is TC, oh no, this is TA. No, this is TA by 4. And this V2, this is TC by 4. No, TC by 2. So we applied V2 P type, no, N type. So what is the next turn? What is the next one? What comes after this? What comes after this?
V7.
So how you choose that V7? So we have V7, yeah, V7 P0N. So it will be how much duration it is? TB by 2. So we have V7 vector. So what is next here? What is next?
V1 POO.
What you're saying? P0N. What will come
Yes.
after next?
V1 sir.
Hmm?
P00.
P00, yeah, good. P00. So that means it will be how much it is? How much duration we need to? PA by 2. So it means it is V1 P type small vector. Okay. So what comes after this?
PPO.
PPO. What is PPO? Yeah, PPO.
Yes. Sir.
No, we must follow the symmetry, right? So we must follow the symmetry, right? So what will come here?
V7.
Hmm? So we have V7 vector is there, right? So this is V1, right? So what comes after this?
PON.
See, if you say that, we'll follow PPO, right? So this is your option, okay? Right? So what comes after this? What comes after this? If this is the case, so you said that this is PPO and its time period is TC by 2, right? Okay. So what comes after this? So what you left with? So V7, right? So that means this definitely it is V0N only, right? Agree? It must be V7 vector only, right? You agree or not? Okay. So now if you change that, so there are two phases are affected here, right? So two phases are affected. So that is one thing. And the second thing is symmetry is lost. It must be symmetrical. So it must be symmetrical. Okay. So if you have V7 vector, so that means you must have V7 vector here, so V2 vector here, and V1 vector here. So that is the symmetrical case, right? If it is not symmetry, again the problem of even order harmonics will arise. So now what you will get here, so P0 N,
N.
okay, so that means TB by 2 period here, so this is V7 vector. So what else here? P0N means, so we have this, right, 00N. So it will be 00N, and it is TC by 2, and this is V2N. Understood?
Yes.
Right. So even though, so there is a chance to use this PP0, right? So we have some trade-off here. Understood? So we have some trade-off here. So either you can sacrifice the neutral voltage deviation, or either you will sacrifice the additional switching, or either you are ready to accept the additional switchings. Right? Understood? So here there is one particular case here, right? So either you can choose 00N, right? Or you can choose PP0, PP0. So that also you can choose. That means P type small vector you can choose. Okay. So if you choose this one, the advantage here is the neutral voltage, right? So whatever some deviation of the neutral voltage is there, right? So that can be improved. Right, that can be compensated, but the disadvantage is additional switching losses, right? It is P0N, right? So that means this phase is affected and this phase is affected. Okay, understood? So this effect is entire thing, right? So this is not for single instant, right? So this is carried for every TS of period of time. So that means you have additional switching or additional switching for every TS period of time. Understood? Additional TS of period of time, you have additional switching. Okay, so that's why, so you have some trade-off here. So either you choose to improve the neutral voltage deviation, or you can accept the change, right? And you will save the switching losses, right? Okay, so this is the one. So 00N, so is selected TC by 2. So what is the next thing? So what is the next thing? 00N, right? So that means 0NN. So this is TA by 4, and this is V1N. Understood? Okay. So this is how a dominant space vector is a dominant small space vector is divided into P type and N type small vectors, right? So this will effectively increase the or effectively decrease the neutral pointers deviation, and as well as it will not further increase in the switching states, right? So if you have any questions here, so we'll stop here, and in next class we'll discuss continue this one.